While the classic web login form is increasingly hardened, database attacks are finding a new point of entry. As infrastructure shifts toward microservices, the vulnerability has moved from the visible web page to the invisible API boundary. We are no longer seeing attackers drop simple malicious strings into a URL bar. Modern injection vectors are heavily disguised, targeting the back-end communication channels that link services together. Legacy web application firewalls are tuned to catch those obvious URL anomalies, but they frequently fail to inspect nested JSON objects, GraphQL variables, or custom HTTP headers where the real payloads now hide. This diagram compares a secure front-end web form to a vulnerable Python Flask API. The code blindly accepts raw API input, fusing it directly into the database query. It fails to distinguish between developer instructions and user data. When attackers exploit these specific endpoints, the system doesn't crash. It doesn't throw a verbose database stack trace onto the screen to reveal the logic flaw. The front end remains entirely silent. It continues to return standard, generic HTTP responses, completely masking the database chaos occurring behind the scenes. This creates the conditions for inferential, or blind SQL injection. Without direct output, attackers must deduce the contents of the database through trial and error. By observing how a silent API reacts to specific probes, an attacker turns the application into an oracle, extracting data piece by piece. Receiving direct database readouts in an HTTP response is known as in-band SQL injection, and it is exceptionally rare in modern architecture. To navigate a silent system, attackers rely on Boolean inference. A standard OWASP Boolean payload is injected to interact with a database table structure. The substring function executes first, isolating the first character of an admin username. Next, the ASCII function converts that letter into a standardized integer for numerical evaluation. This sets up a binary decision. Is the first character's ASCII value exactly 97? The API passes the result back. True generates an HTTP 200 success. False generates a 404 or 500 error. Attackers don't type these requests manually. They script automated loops, rapidly iterating through the entire ASCII table until they hit an HTTP 200 success. Once the first letter is confirmed, the script shifts to the second, then the third. Letter by letter, it builds out passwords and entire database tables. By exploiting the application's basic arrow handling, the attacker reconstructs relational data based purely on minor variations in HTTP status codes. But what happens if developers configure the API to return the exact same response, regardless of whether the database query evaluates to true or false? When absolute response uniformity blocks Boolean inference, attackers shift to time-based inference. A time-based payload is positioned above a timeline, commanding the database to execute a literal pause if the condition is true. The timeline expands. An intentional 10-second delay on the server response confirms the query's truth value. If the evaluation is false, the query executes instantly, returning a fast HTTP response. Because this method relies on measuring latency, it requires a massive volume of highly repetitive queries to filter out natural network jitter. Time itself becomes the data channel. Obfuscating HTTP responses is useless against an attacker patient enough to measure latency. Developers often try to block these attacks by configuring firewalls or regex filters to blacklist specific keywords, like union or select. Attackers bypass this using SQL signature evasion. A standard payload mutates into fragmented pieces using inline comments. The firewall sees the fragmented text and lets it pass. But database engines parse those inline comments and ignore the obfuscation, reassembling a perfectly valid SQL command. Attackers also use hex encoding, converting plain text into hexadecimal strings to bypass basic filters. This creates what is known as the semantic gap. A vulnerability exists because the security filter parses data differently than the backend engine executing it. Filtering fails because a single command can be encoded in thousands of ways. A simple blacklist can never account for every possible mutation. Defeating inferential extraction requires changing the architecture of the database query itself. Replacing vulnerable string concatenation with parameterized queries establishes a strict control plane. The SQL logic framework is precompiled. User input is assigned to a separate data plane, slotted into an isolated container. Malicious payloads become inert because they cannot alter the literal logic structure. Object relational mapping frameworks implement this parameterization by default, but custom raw queries still require caution to ensure the logic and the data never mix. The final layer of defense is the principle of least privilege. Restricting database accounts to read-only permissions limits the blast radius of secondary flaws. Architecting backend systems to structurally isolate user input from execution logic makes malicious payloads harmless. This prevents attackers from ever turning the application's response into a usable data channel.